So very warm welcome to you, Matthias. Matthias Geilhufe, I hope I've said that correctly. Yeah, who's originally from Halle in Germany. We were just chatting earlier, and he's a physicist. He did his PhD in Stockholm, and now he has a reasonably large group at Chalmers in Gothenburg, consisting of some number of PhD students and postdocs. He's a Forskarassistent. I didn't realize that actually still existed, but it does at Chalmers. Yeah. And Matthias was one of our first two winners of our Horizont Award, which we had started in 2023. And this grant is something I think we're very proud of in Physiographen, because we can do things with our money that is not possible at VR or other normal funding agencies. So we can decide ourselves how we're going to use this money in the best way we wish. And this particular grant, the Horizont, that is a sum of money which is designed to encourage people to think outside the box, I think is the best way of putting it in English, where it recognizes, for instance, that some of the best ideas in science arise at this kind of bubbling interface between disciplines. And this grant encourages applicants to think outside the box and to think interdisciplinarily and to come up with brand new ideas that are so sometimes completely crazy, it seems, at least initially, that normal funding agencies wouldn't necessarily be interested in looking at them. And I think that's one of the great things about our society, that we've got the financial capacity to be able to support projects that are a little bit outside the normal. In other words, allow people to think outside the box and hopefully make great discoveries. And yours was awarded, your project was awarded, Matthias, in heavy competition, because there are lots of people who apply for this grant. So congratulations from the society. I'm not going to take up any more of your time. As I said, Matthias is a physicist, and he's going to tell us for the next 40 minutes or so about ultrafast thermodynamics. Over to you.
All right, thank you very much. Thank you very much for the kind introduction, and thank you very much for giving me the opportunity again to come here and to present my research. It's a great honor for me to speak in front of the Royal Physiographic Society in Lund. And of course, it's also a great honor for me to have received this Horizont funding. And indeed, as you just mentioned, it has been, for me, a very important cornerstone in building my group, actually. So just basically to briefly mention that, I'm currently an assistant professor at Chalmers, and I'm heading a group which I call the Quantum Materials Theory Group. So right now we are about 9 people. And just to basically acknowledge also everybody in my group, so these are the people who do most of the work that I'm going to present today. And very roughly, basically, as the headline already says, I'm a theoretical physicist. I'm working in a field which is called condensed matter theory. This usually sounds a bit, let's say, unfamiliar to many people, but it actually turns out that condensed matter physics is one of the biggest areas in physics right now. So about 80% of all physicists are condensed matter physicists. And if you think a bit what it means, it basically covers all sorts of phenomena which are condensed, right? So that's why it basically goes from biophysics, from soft matter to crystals, material science, and all of that. And I'm a theorist, so we cover, like we describe a specific type of materials, which we call quantum materials. I will talk a bit more about that in a second. But roughly, let's say, 3 research areas that we cover in my group are ultrafast dynamics in these materials. So today, one can basically excite quantum materials on very short timescales using laser pulses. That is mostly what I'm going to cover today. But then my group is also very much interested in symmetry principles in quantum materials. Symmetry is a fantastic phenomenon which occurs in nature and art and pretty much everywhere. on our planet, and of course also in materials, and it can be exploited and functionalized and everything. And then we also discuss novel and functional quantum materials. So we also in that sense try to go a bit outside of the box, because if you go basically to novel materials, you might just find phenomena which we haven't even been aware of, right? But in the interest of time, I will focus on one topic, and that will be ultrafast thermodynamics, and that is also the topic which is basically in connection to the Horizont funding from the Royal Physiographic Society in Lund. So what I thought is the following, before we basically go into the hard science part of this talk. Let's just take a look at these individual terms and ask ourselves a bit what they mean, and can we maybe familiarize ourselves with these terms. So if you talk about ultrafast thermodynamics, then I thought let's start with the term thermodynamics, because that is also something which from a historical perspective probably came first, right? And in particular, today we can pretty much say that thermodynamics, if you think of it basically as a theoretical framework, one can say that thermodynamics has been pretty much the conceptual breakthrough or conceptual theoretical breakthrough which lay behind the development of the Industrial Revolution. And basically the Industrial Revolution, basically starting in different countries pretty much at different times, but let's say in Central Europe about 19th century, has pretty much shaped the world as it is right now, right? It has led to the fact that basically, for instance, countries like Sweden are on the economical status that they have right now. And one of the basically key developments from our today's perspective, it sounds quite simple. One of the key developments was the steam engine, actually. And the steam engine is basically a device which has a simple principle. You basically heat up water, it becomes to steam, it starts to expand. You can basically produce work in the machine, you can cool down, and then you basically start the cycle again and again and again. And these type of phenomena, they have been discussed basically in like in the framework of thermodynamics with the Carnot cycle and others. And I just wanted to also put this picture, which I found quite interesting, to the left. So this is an old copper print which was made around the time of the Industrial Revolution. So pretty much when the first factories were built, then people felt like, okay, this is now the technological breakthrough, and then a lot of art basically now suddenly contained buildings of factories and of chimneys with lots of smoke and all of that, right? And it didn't take them very long to realize that it probably also has some downsides, right? And today we are facing them and try, of course, to go away from this type of technology to a greener technology. Just to basically build on that principle, so thermodynamics, as I said, was pretty much built from the knowledge of building machines. It laid the foundations to novel engineering and so on. But it had quite a lot of this like phenomenological background. People said like, okay, there are quantities like heat, like work, like volume, pressure, temperature, and so on. And they described basically the physics based on that. And slightly later, there was another, let's say, conceptual breakthrough in the physics realm, and that led to the development of the statistical physics. And the basically idea of the statistical physics was, can we describe all of these macroscopic phenomena in terms of microscopic principles, right? So you take, for instance, I tried to show this on the example of this piston. So the piston is, for instance, filled with some gas. I heavily underestimated the number of gas molecules that you have in the piston. Usually it's something like 10 to the 24 or so, right? So I didn't want to draw that, but the message that I wanted to give across, basically, you have a finite volume where these gas particles fly around. They all have kinetic energy. Their average kinetic energy we start to call temperature. And then these gas particles, as they basically fly around, bounce off at the boundaries. They also basically like have a force on the surface, and that basically gives rise to quantities like pressure and so on. So that was basically the breakthrough which made people understand, okay, out of microscopic phenomena, if we now understand which particles we talk about, how they might interact, independently basically of classical or quantum or whatever the nature of this particle is, basically gives rise to macroscopic phenomena if I take their statistical average. And that is a fantastic theory which is pretty much unchanged until today and heavily exploited in all sorts of applications. A specific quantity which I just very, let's say, phenomenologically try to introduce in this context is entropy. So before we talked about, for instance, temperature as being the average kinetic energy of the particles, volume, basically have some knowledge like the volume that the particles basically encompass. And then basically entropy is a bit of the more abstract quantity. It is connected to basically the probability of all sorts of microstates that you can have in such a system. But if you want to think of it a bit more in the phenomenological terms, then basically entropy is a measure of irreversibility. And on this picture, basically, I show you a cup which is filled with water. So this is an experiment that I have done as a theorist. So I filled it with warm water to make it a bit faster, and then I put like a couple of droplets of yellow ink into the water. So that is what you see to the left. And then if you just basically leave this glass alone for a couple of minutes, then basically the ink will fully mix with the water, and then you end up with the situation on the right. And as we basically know from our everyday knowledge, it is very, very unlikely that we start with the situation to the right and wait 10 minutes and end up with the situation on the left, right? So inherently to these systems, there's a measure of irreversibility. So as basically time goes, the system tries to maximize its entropy, and that is basically also what defines a state which we call equilibrium. That's the state of maximal entropy. So basically the system doesn't want to leave this situation again, and that's the situation where basically the degeneracy of equally probable states is highest, pretty much. Okay, so that was basically some introduction to thermodynamics, and now I want to make a jump basically to a development in a field which is actually outside of my area of research, outside of condensed, well, let's say kind of quantum materials, let's put it like this. And this is a development which took place very rapidly, let's say in the past 20 years. Here I basically heavily underside, so it's a super active research area with many fantastic research papers. But very roughly what it does is it's the field of stochastic thermodynamics, and it is now a field which pretty much goes from, let's say, macroscopic phenomena back to microscopic phenomena. If you, for instance, think of systems which have very different scales, so take, for instance, Brownian motion as an example. You have a fairly big particle in a glass of water, then this fairly big particle will have some erratic motion because all of these water molecules start to interact with the big particle, right? So in a sense, you still have 10 to the 24 particles involved, but there's one particle that you are primarily interested in, and that is the big one. So now you can basically think, let's say, kind of next level of sophistication. What is if this big particle is a living species, right? If it could be some tiny bacteria or some algae or something. And many of these, let's say, tiny living species, they have some sort of internal motors, so they try to move, or it could also be like a plankton or something. And they usually want to get from A to B, right? Because there might be some food, or there might be light, or it might be warmer, or some condition might be better for them at that point. So they try to get from A to B, but still they are living in this kind of stochastic background. They are all the time pushed by many water molecules. But what happens is actually one was able to use this kind of stochastic motion of these particles basically in the coexistence of the force to rederive thermodynamic quantities such as entropy, entropy production, heat production, and work. So now in that sense, for instance, if this particle wants to move from A to B, it produces heat, it produces entropy in the water. And one can basically define all of this entirely on this motion of this particle. And that was a fantastic, basically, development. And as I said, has been one of the most active research areas in non-equilibrium statistical physics in the past 20 years. So now I want to basically leave that part for now, and I want to switch to something completely different, right? So now we talk about ultrafast dynamics, and now we talk about quantum materials, right? So first of all, what are quantum materials? How can we envision materials and so on? And I want to start again with another picture and a phenomenon which we call emergence. And emergence means that basically an entity or a property is observed, or an entity is observed to have properties its part do not have on their own, right? And here's a beautiful example, basically, again, in the macroscopic world. This is a flock of birds, and together they form this huge bird. And it actually turns out, I mean, I'm not a biologist, but it turns out that, of course, the birds don't do this by chance, but they actually have a reason to do that. Basically, it's for them, it's a way of protecting themselves. So it might, for instance, happen that bigger birds come and want to eat basically the small birds. It's like an eagle or something. And as soon as basically the small birds start to form these kind of interesting patterns, they change the aerodynamics around the big bird, and the big bird just falls down. So they can basically protect themselves with this collective phenomenon. And if you want to describe this physically, then you can say, okay, all these birds, they have an interaction. They want to be close to each other. Again, they don't want to be too close, right? So there's an attractive interaction if they are maybe like 5 meters apart, and there's a repulsive interaction if they are 10 centimeters apart, then they might want to step back. And the same basically happens in materials. So you can think of materials as being compositions of, again, 10 to the 24 ions with 10 to the 25 electrons. And there's no way that we can basically describe every individual particle at once. And maybe it's also not so interesting. Instead, all of them together form sometimes macroscopic properties that we also want to exploit in technology. But sometimes they also form macroscopic quantum properties. And one of the most familiar ones or most known ones is actually superconductivity. This is a state where a material or a metal at low temperatures suddenly completely loses resistivity. So it becomes like a perfect conductor. And that is a phenomenon which can be entirely described with quantum mechanics. That's quite interesting. It was discovered in 1911, again, basically on this premise of as soon as you do something new, you find something new. That was the time when people were first able to cool down to cryogenic temperatures, so something like below 4 Kelvin or so, and suddenly they see this kind of phenomena occurring. Nobody knew what it is, how it comes about. And it was actually about 15 years, or let's say 13, 14 years before, for instance, the formulation of the Schrödinger equation, which builds a kind of novel, modern understanding of quantum mechanics. They found basically the quantum property before. Explanation of this phenomena took until mid-50s, and there are still cases that we don't understand until today. And then there's other classes I just briefly want to mention. There is superfluidity. It's the same phenomena for liquid. At low temperatures, liquids become perfect liquids. They just flow without resistivity. So if you pour them in a cup, they just leave the cup again and rin down. If you start to steer them, they will basically have vortices forever. They never stop and so on. And more recently, there are so-called topological materials, Dirac materials, where you have emergent relativistic physics. But very importantly, let's say in the past 2 or 3 decades, basically laser technology and so on has been on the level that we can now study these phenomena in the time domain. And that is pretty much where I want to get at. So this is like a schematic. As I said, materials are very complex. They have many, many ions, many, many electrons, but they follow, let's say, straightforward building principles. And one of the building principles is like, the ion can sit on a specific lattice site. So you can change the lattice of a crystal, you might change the properties. The electrons might occupy very specific orbitals, right, depending on the species of the periodic table that is involved. Electrons carry a spin, electrons carry a charge, ions carry a charge. And all of these phenomena basically together, they build the macroscopic phenomena of the crystal. And now I can basically come with a laser pulse, and I can try to tweak these individual properties. I can try to change the lattice structure, I can try to change or excite very specific orbitals, I can try to create so-called electron-hole pairs, I can excite electrons, I can work on the charge dynamics, on the spin dynamics, and interestingly, and this is basically an important property, all of these phenomena, they take place on slightly different energy scales, and so they also take place on slightly different time scales. That also means that if we have basically different laser frequencies available, we can tweak these different properties in a different way. Okay. Here is a summary of a very nice experimental paper. This is by De La Torre and others, which just tries to make this point again and also to say basically on which sort of time scales we are working on now. So it's a bit difficult to read, but it starts at 10 to the minus 9 seconds, so this is nanoseconds, and goes up to 10 to the minus 18 seconds. So that is pretty much the realm that Lund has become very famous for, right, for obvious reasons. And I will mostly talk about the realm about 10 to the 12 seconds. So 10 to the 18 seconds is basically the realm which studies the electronic dynamics. And if you go a bit slower, then you are in the realm of basically lattice dynamics and so on. And there are different probing techniques. There are optical techniques, so you can excite the material, you can shine a probe laser and basically try to read out properties. There are scattering techniques where you again shine light and you read off the scattered signal. You can try to measure some sort of transport properties. You attach a voltage, you try to read off any types of currents. There are charge currents, spin currents, orbital currents, everything. There are scanning probes where you basically, this is scanning tunneling microscopy, where you come with a basically atomic needle very close to the surface and you try to read off basically how the materials look. ARPAS is yet another basically laser-based technique which reads off electronic states and so on. So basically, the message of this slide is a lot is possible, and a lot has been studied. So that means, can we now bring those two fields together, right? So we know there's a fantastic development in non-equilibrium statistical physics. We know we can basically control and probe quantum materials at extreme time scales, right, from nanoseconds to attoseconds, basically. And this is also basically when we excite them, we bring them inherently out of its equilibrium state, right? Because we force the material to be in some state that it doesn't want to be, basically. And non-equilibrium physics turns out to be extremely challenging. Non-equilibrium or like time-dependent quantum mechanics is a very hard field. So then the question is, how do we treat these systems? And the idea, which was basically also connected to the application of this Horizont funding, was that can we basically merge this one? If we know there was thermodynamics, as I mentioned at the beginning, then it led to the development of the statistical physics around 1900, basically in the microscopic regime, and the stochastic thermodynamics about 25 years ago for small systems, single particles. Can we basically borrow this methodology and bring it into this ultrafast regime, where we now, instead of the bacterium, talk about materials and material excitations and so on. So we have to develop somehow this connection. And now basically I will get a bit more technical, but I hope that it still becomes clear basically where the connection is, right? But I will slowly get more technical. So just to remind you, basically, the situation that we started with is the bacterium. This is the picture A, right? It wants to go from A to B, and we said, like, okay, this process is now understood. We know how this process produces entropy. What does this process have to do with the material which I show in picture B? Well, you know, the bacterium has a motor. That is this flagella, which I tried to draw here. Now you can think of the laser pulse as having the same function. And then instead of the bacterium now you don't talk about the single atom, but instead you talk about this basically collective lattice vibration that you have in the system. And actually, if you take a look at this one, it has a very similar dynamics, because this lattice will interact with everything else that you have in the crystal. That will lead to the fact that this lattice vibration will decay at some point. It will dissipate its energy into the bath. But if there is dissipation, then there's also always fluctuation. So then there's also always randomness to this motion. There's always stochastic motion to this process. So then the claim was, if it works for the bacterium, it should also work for the laser-excited lattice excitation, for instance. There's an equation, is a classical equation of motion, which looks very similar like the bacterium equation of motion. It's a so-called Langevin equation. It's an equation which discusses stochastic processes, and it contains basically a second derivative of the phonon. That's basically the acceleration of this mode. It contains the dissipation term. It contains basically its frequency term. It's a harmonic term. It contains the laser pulse, and it contains the noise, the stochastic noise. And basically the kind of first work that we did was published last year, beginning of last year. It was a collaboration with Lorenzo Caprini and Hartmut Löwen. And both Lorenzo and Hartmut, they are actually experts in this stochastic thermodynamics. And then basically the idea of this collaboration was, can we basically bring those two fields together? And it turns out, okay, now this is again another equation, but there's a reason why I want to show this one. So first of all, now we can talk about the same entropy production as I mentioned at the beginning for the stochastic process. We can pretty much use the same ansatz. I want to compare basically the stochastic process. How does this stochastic process, what is the probability of a certain path forward in time against the probability of the same path backward in time against the applied force? And that basically quotient is a measure of irreversibility, so it's a measure of entropy production. And after basically a longer derivation, one can actually come to the conclusion it takes a quite simple form. The only thing that basically that we have on the right-hand side is pretty much the velocity of this phonon mode and the force of the laser. Okay, so this is two information. And it actually turns out that these are two information that people already have. There are experiments, so this is an example from the SLAC facility in Stanford, where an experimental group studied the lattice vibration of one specific material that's called strontium titanate. That's a so-called perovskite material. And what they do is the following. They basically use two different laser beams. One is a terahertz, so this is basically on the order of 10 to the minus 12 seconds. That is basically the pulse which acts on this lattice vibration. So with that pulse, they start to excite the lattice. And then they have a second laser, and that's a hard X-ray laser pulse. And that is the probe pulse, where they measure a scattering, basically standard diffraction scattering for the crystal structure. But now they do this time resolved, and they do this time resolved on a crazy time scale. Basically, every 30 picoseconds they have a pulse. So every 30 picoseconds they can read out what is the actual crystal structure by now. Okay. And if they do this experiment for strontium titanate, then what they can actually do is they can measure exactly what we are studying. They measure the basically motion of this phonon mode. So you see it basically oscillates a bit like in this picture that I showed at the beginning. But you can also see that there's a lot of noise, right? So it's obviously there's some stochastic process involved. So that basically underlines the claim that stochastic thermodynamics might be a very good framework to study this. And then basically we developed our theory. We were aware of this experiment, so we could basically reuse some of the data that was produced. And I'm now showing a couple of plots. Plot A is basically the laser pulse. So the blue curve is the experimental laser pulse. Remember, there were two quantities that we want to know, the laser pulse and the velocity. So the laser pulse is pretty much known trivially, so that is basically what experimentalists use before they even start to study the material, right? And then the second thing is basically the phonon. So you can now take, again, this picture, you make a so-called Fourier transform, so instead of taking a look at the time scale, you start to take a look at the frequency of the oscillations that you see. And then you see basically very characteristic peaks, which are connected to very characteristic modes, plus a couple of noise in the background. And we could basically show that if you now put those two things together, you actually have a tool to read off entropy production in the material. And it's a very interesting thing because entropy is a quantity which has been known for more than a century. But you cannot really go and take a bucket of water and say, like, okay, now I take a device and measure its entropy. Right? You can measure the temperature, you can measure the volume, but measuring entropy is in that sense not possible in that example. And here we basically show a scheme how you can measure entropy production on the microscale, basically from basically standard experimental data. And entropy production is also closely connected to heat production. So we basically have a theory for how do heating processes take place on this crazy time scale of 10 to the minus 12 seconds. Okay. And then, of course, now it becomes a bit more technical. If you want to stay on this example, then there are a couple of things that, like, this is basically our fruit fly. We know, okay, we have one example, it works. So now how can we extend it? How can we show that there's a bigger principle behind? So I said there's a couple of assumptions that you can take. First, you say you want to start on working on a phonon. So you can lift that property. You can say, can we work on another property? You can say the noise has a very specific property. The easiest property is so-called white noise. So it contains basically fluctuations with every frequency. That is in a sense unphysical. So you can think of lifting this condition. And that is pretty much what I'm trying to outline, at least here. It turns out that at Chalmers, right next to my office, there's the office of Paul Erhardt. And Paul Erhardt is a full professor at Chalmers, and he's an expert in molecular dynamics simulation. So what they can do is they can take a computer and model basically dynamics of atoms. So they take, I don't know, 1,000, 10,000 atoms, put them in a box, and then they check basically what is their ground state. And then from this basically discussion, they started to make a simulation where they say, like, okay, what happens if we now basically excite them with a specific mode and then we let it go? So we try to basically understand. To the left, you see the so-called phonon band structure. It contains a lot of these spaghetti lines. So each line corresponds to a very specific mode with a very specific frequency and so on. But there are 4 modes which I highlighted, and 3 of them are modes that one can talk to with a laser field. And basically those modes start to couple to each other, and that is what I'm showing to the right. So if we think of driving the mode, which is the B mode, the A mode, then we can see that there are basically 2 modes that are very strongly affected, and 1 mode which basically doesn't do anything. And now Yulong Shao, who is a postdoc in my group, he started to basically take this theory of the stochastic thermodynamics and extend it basically for this assumption that what happens if you don't have white noise, but if you only have very specific modes that you can couple to. And he basically, out of this assumption, managed to write down a different version of a Langevin equation, which is now a bit more difficult. It has a so-called non-Markovian noise, so it has a noise term, it has a dissipation term which has memory. And then basically he discussed, okay, how does the noise look? And came to an equation which on the first hand looks a bit difficult, but then it has one property which is very important, and this is the D. And this D is a property which we call density of states. And it basically connects to this phonon band structure that one can calculate with a computer. It pretty much asks, if I take a specific frequency, how many excitations can I find at this frequency? How many different phonon modes are there? And Yulong could show basically that this noise-noise correlation is dependent on that one. And Erik Fransson, who is a researcher in Paul Erhard's group could actually calculate that and could actually calculate how does the density of states look for the system. And with that, basically, we could bring together this kind of analytical theory of the stochastic thermodynamics with a real computer simulation, where we now can basically study this ultra-fast thermodynamics again on these time scales. Okay? So I said now it becomes a bit more technical. Right? But you see, the main message is now what I'm trying to show you is, right, we have now this new approach, and now I'm trying to show you a couple of the examples where we can go with this one. Another one is basically, as I just said, if it works on the lattice, it should work on everything else, right? So then what is another good degree of freedom that we can think about, and that is magnetism. So you can just think of your conventional fridge magnet, right, which we all have in our homes. These are ferromagnets. They have a finite magnetization. And I can control this magnetization with temperature and so on. So you should not heat up your fridge magnet. Then it will not work anymore, at least at some temperatures. So we can control that. And again, there is a basically ultra-fast scheme where one can basically excite magnetization. And now I really don't want to stress the equations in too much detail. What I really want to tell you is that if there is an equation of motion for a phonon, there is also an equation of motion for magnetic degrees of freedom. They look very different on the first side. The equation behind is called Landau-Lifshitz-Gilbert equation. But you can again extend this and say like there's a stochastic component. And then this is a work which was done by Finja Tietjen, who is a PhD student in my group. So Finja could show basically in a similar approach, if you again basically use this ultra-fast thermodynamic setup, that you can come to an equation for computing the entropy production and the heat production if you were to control the spin of a magnet on very short time scales. And then of course again the question is, now we have a theory, is this something which has any connection to reality? And it actually has. It's again the same principle. As I told you, like ultra-fast dynamics has been developed independently of thermodynamics. So people already know how to control spin degrees of freedom. And there are experiments basically where they excite the magnetization with a magnetic field. Okay, now it's I forgot to put the picture of what exactly it is, but the orange line is basically a magnetic field from a laser pulse from an experiment, and the green one is our simulation where we try to model basically the same quantity, so we try to fit a shape which looks quite nice. Then we could put that into our equation of motion, so we can basically simulate how the magnetization would change, and the experiments can measure how the magnetization can change. And then, of course, out of these two information, again, you have your laser, you have the motion, so you also know what the time derivative is. You can compute how much heat do you produce in this process, right? And that is a quantity which is important because if we want to work, for instance, on magnetic degrees of freedom, so keep in mind that all of our storage devices today are pretty much working on magnets, and we want to control them in very short time scales because we want to basically transfer data as quick as possible. We usually don't want to heat them up, right? So we want to have some knowledge basically how does heating actually in magnets work. Then another extension is basically quantum. So far, even though I talked about quantum materials, I always showed you classical equation of motion, which basically mimic these excitations. And this is true if you, for instance, come with very strong laser fields, then many of the dynamics in the materials, they start to take a kind of classical form. But again, just to show, we also started to look into how to extend this to a full quantum mechanical picture. Then basically the difference is that, for instance, if you think about a harmonic oscillator, so you just take your pendulum, classically it will basically go back and forth. But quantum mechanically, this is not the case. Quantum mechanically, there are only very specific energies for the pendulum allowed, that the pendulum is allowed to have. And then we can also not really track the electron. We can just say what is the probability of the electron to be at a certain position. So for instance, the lowest lying state would mean that the classical pendulum would just hang. And the quantum mechanically lowest lying state is somewhere basically around the center. And then for an excitation, for instance, if the pendulum goes back and forth, there's for instance, the first excited state basically has probabilities on 2 positions. So we can use these quantum properties, and then it was anticipated, but it turned out not to be very easy. But we can now, instead of talking about the classical quantity for entropy or heat production, we could write down a so-called quantum mechanical operator. So we can say as the energies basically go in steps in the quantum systems, also the production of heat and entropy goes in steps in the quantum system. And that is probably the final example or final application, or final extension of this whole thing, is that now we pretty much go back from one collective mode to something macroscopic. Again, if you think, for instance, of magnetization, as I told you, there's a fridge magnet. It has a global magnetization. But really, if you think about this, like, let's say, more microscopically, you can think, okay, can I go to different positions on this magnet? And could the magnetization be slightly different? Then magnetization starts to become a function of position and time, if I start to drive it. So it becomes a field. And I can start to talk about basically macroscopic properties, macroscopic phases in materials. And there's a quantity which is called the free energy. For chemists, there's also a quantity which is called the Gibbs free energy, which is in reactions often more important. But for physicists, actually, the conventional so-called Helmholtz free energy is sufficient, and that's a combination of the internal energy. So basically, each configuration has a certain energy, and an entropy term. At low temperatures, if basically the entropy term is not around, the state wins which has the lowest energy. At high temperatures, if the entropy term is around, the entropy term will win sooner or later. There's always a transition temperature. At some point, the system doesn't care about energy anymore. And it turns out that basically for these kind of systems, like if we have a free energy in terms of a so-called order parameter, in terms of a magnetization, in terms of a polarization or whatever, one can write down a dynamics for this order parameter out of this free energy field. And out of that, we again derived a very similar form for the entropy production. So there seems to be a basically unifying pattern which goes over very different types of phenomena. This is something that the master student, Erik Karlsen-Öhman, is working on right now. And he develops actually quite intense numerical tools to study these field equations. And again, to the right, I want to show a picture of an experiment which we have in mind. There is a group also at Stanford, which basically shows that with a laser field, you can control the so-called energy landscape of a material. So they now talk about ferroelectricity. That is a situation where basically atoms spontaneously want to slightly displace and basically induce local dipole moments. And they basically show that if they come with a very short laser pulse, the atoms can be stuck in this configuration, so they don't want to go back. And we believe that basically entropy production is a basically key concept in this process to understand. So with that, I would like to thank you again for the invitation. I see that the second part was maybe a bit technical, but I hope it was still okay. I want to acknowledge basically the contributions of my group and collaborators at Chalmers and Paul Erhardt's group. And currently we are also discussing about experiments together with the group of Niccolò Macaferi in Umeå and his PhD student Clegg, and then collaboration with Lorenzo and so on. And of course the funding from Royal Physiographic Society. And with that, I thank you for your attention.
Anybody like to ask a question? Per. Always reliable.
Thank you so very much. Exciting, although I am a layman. Now, this is a question to enhance my understanding, so to say, one way or another. So entropy is a macroscopic phenomenon.
Macroscopic.
Macroscopic.
Yes.
Right?
Yes.
And you argue here that you have quantized entropy. Isn't that, phenomenally interesting?
I think it is impressive. I think so. But one needs to be a bit careful here because we talk about the entropy production in these processes because basically, let's say you are in a situation where you are out of equilibrium and you want to go to equilibrium. And equilibrium is the situation which is defined by the state with maximum entropy. So in some applications, you don't care so much about what the exact value of the entropy is, but as long as you still increase entropy, as long as you still produce entropy, you're still on this path. And we show basically that this entropy production is quantized.
Yes, fine, but still, I find it remarkable that you can actually talk about a macroscopic phenomenon or macroscopic property of nature, namely entropy, as being quantized. I think that is quite remarkable.
I think so too. I think so too. Yeah. Thank you.
Thank you very much. Another layman's question, being a computer scientist. I was really impressed by the approach and how you bridge between theory, simulation, experimentation.
Right,
Can you comment more on that, the type of both collaboration and is the flow symmetric, or which of these tend to be? You gave examples of where experimentation show phenomena which you now can begin to explain.
Yes. So
is that the opposite path sometimes, or what's more common?
Yeah. No, thank you very much for this question. Basically, let's say I would say we are still quite at the beginning of this whole development. But for me, it was very important, let's say, from the beginning to have a very direct connection to experiment. So what we did so far in these let's say, projects that we worked on was that we tried to find experiments which pretty much measure the ingredients that we need, right? But these experiments were often done, let's say, a couple of years ago, and they were studying something totally different, right? They were not talking about entropy or heat or so. But since the data is so nice, and since data is now quite often published together with the publications, then we could actually use it and to show that these experiments pretty much already have all the information that they need to talk, for instance, about thermodynamic processes in the context of measuring. And as I said, that is quite often quite important. That, for instance, in this example of the magnetization, you might see that the numbers are very small, and that is also connected to the fact that they wanted to discuss a certain dynamics, and they wanted to avoid that the structure heats up. And experimentalists are extremely smart. They kind of have intuition of how to do this. But ideally, and that is also basically in the collaborations that we are trying to set up, for instance, with Niccolo Maccaferi's group and others. Ideally, we want to find basically this describe novel phenomena and basically guide a bit like what could be interesting to take a look at.
So I'm from the laser side, and I've been dealing with lasers for a long time, and the field of ultrafast has been always there.
Yes.
But it has changed by orders of magnitude every decade, from being nanoseconds to picoseconds to femtoseconds and attoseconds. So when I saw this topic, ultrafast thermodynamics, I was just wondering, what is the time scale for ultrafast thermodynamics? On your slides, most of the graphs where you show the time evolution, they were picoseconds.
Yes.
But you were mentioning in the beginning that you could excite it with attosecond pulses.
Yes. Yeah, no, thank you. It is a bit of the question how we want to define what does ultrafast actually means, right? Or what does it mean? Let me phrase it that way. It is true, picoseconds on the time scale, like picoseconds is 10 to the minus 12, attoseconds is 10 to the minus 18. So picoseconds is extremely slow compared to attosecond physics, right? It is extremely slow, but let's say the point that I want to make is that the specific phenomena that you want to discuss, they live on very specific time scales. So if you come with the attosecond pulse, you will not trigger the lattice excitation, for instance, right? So typically what you do is you have this pump probe set up. So you have a pump where you trigger a very specific degree of freedom. And then you have a probe, which is 2 to 3 orders of magnitude faster at least, right? So for instance, attosecond physics you need because the basically electron energies on the EV scale, they are basically 3 orders of magnitude slower, so that you can basically with the attosecond physics measure the excitations of the electrons, right? But then in this process of basically electron excitation together with their pulse, you should be again able to define something like ultrafast thermodynamics of electrons. That is the claim. But my definition of ultrafast is also that basically what is the pulse width that you involve, right? So you have very few cycles. So you have a very kind of short excitation on the individual time scale where you live.
Other questions? Yep.
I have 2 questions. One is this some biomedicine area, not physics, but is this stochastic entropy, has it been applied to movements of molecular particles inside cells?
So that is
show the flagellar bacteria, but you can think of there's a lot of movement going around inside the cells.
So now this is basically outside of my expertise. So I cannot make a qualified statement, but it has been discussed on these examples, I'm pretty sure. It has also been discussed in the context of chemical reactions and so on.
Very general, I been reading a little book by a physicist called Carlo Rovelli on time, and he claims that time doesn't exist. The only equations where we perceive time is the second law of thermodynamics and development of entropy, but the fact that we perceive time is that we looked at reality a little bit blurred. That's what he says. So what do you think of him?
I don't know
Very interesting.
it is. I don't know the exact book, to be honest, but I'm to some extent aware of some of this discussion that goes around. So I can maybe say a couple of things which I'm aware of. So there are a couple of parallel threads. So one is basically that, as I told you, entropy always wants to increase, right? So with that, entropy is basically a so-called monotonic function in time. So that means if now, as a theoretical physicist, if two functions depend on each other and have the same property, they are essentially the same quantity. So instead of talking about time, you could talk about entropy, right? So as basically the fact that entropy increases pretty much defines your path in time forward and restricts you from going back. Interestingly, on the nanoscale, entropy production fluctuates due to the stochastic origin. So that means basically for short time scales and on the nanoscale, you lose the direction of time. So you get a bit of this fuzziness. But if you zoom out, the direction of time becomes clear. Quantum mechanically, it's yet another difficulty because there is, like, first of all, we have something like relativity. From relativity, we know that basically time and space are inherently coupled. And you can pretty much transform between the two. So then time becomes gets a very different, let's say, again, a very, very, very different interpretation. And right now, people are actually discussing if quantum theory is pretty much the origin of everything. And there's a theory of emergent space where you can say if you take serious the mathematical foundations of quantum mechanics, that this is defined in a so-called Hilbert space, then you can actually basically, let me go back to this picture. You can say in the same way basically as the birds produce the big bird, the complexity of all quantum states present, they actually produce space and time as an emergent property. That is actually something that we discuss. And in the context of the quantum field theory, it makes a bit more sense actually, because then these quantities, they don't really play that big of a role. I don't know if that helps or puts more confusion into this field, but it's a fascinating thing.
Any other further questions?
Thinking about the comment you made on that the entropy increases as a function of time, or that could be a measure of time, but that is only true. I mean, if you look at the whole universe. So, yes. Whereas here you're studying specific systems, so where in principle the entropy could decrease, right? Exactly. Or how do you take that into account?
You can have these processes, and that is also something which is in a sense very familiar to us. If you produce work, or if you apply work to a system, then you can decrease entropy. And that is, for instance, what happens in the flowers, right? They absorb carbon dioxide as a very high entropy molecule and produce sugar together with the light they get from the sun as the work. And then they produce basically a low entropy molecule. And that one can be burned to go back to a high entropy molecule, basically. So these processes exist, yeah.
Yeah, because I mean, the reason why we can uphold to keep the entropy down on Earth is because of the influx of heat from the sun.
Yeah. Yes. And I think these processes should exist in a similar way on the nanoscale. But I haven't worked on this yet, to be honest.
No? In that case, thank you very much, Matthias.
Yeah, thank you.